All right, this is question number 6 from the 2000 AP Calculus AB exam. This is a differential equation FRQ, and they started off with the big point value here for part A. Just find the solution to it, satisfying f of 0 equals 1/2, right? The solution to this differential equation, which is a quotient here of 3x squared and e to the 2y, which is a separable differential equation. So first we'll just multiply that e to the 2y over to the left-hand side, separating the variables, and the dx over to the right-hand side, giving us e to the 2y dy equals 3x squared dx, right? And we call that separating the variables, and that's always going to be worth 1 point when you have a separable differential equation to solve. And you almost certainly always get a separable differential equation for the differential equation FRQs, almost always. The next couple points are for correctly taking the antiderivatives. Now, e to the 2y, hopefully you're at the point now as you're preparing for these differential equations that you can do this integral that's a u sub quickly in your head. But if not, we're going to write it out. It's e to the 2y dy, and I'm going to let u equal that exponent of 2y. So du is the derivative of 2y, which is 2 dy. So what I have to do, again, is I have to put it at 2 and a 1/2, giving me 1/2 the integral of e to the u du. And of course, that 1/2 can be inside, and I can write this as just 1/2 e to the u when I integrate, right? Because if I integrate e to the u, I get e to the u. And of course, u was 2y. Normally, we'd add a constant there, but since the other side is going to have a constant also, the two constants on each side can be subtracted from one another to just leave us with a singular constant on one side, which we'll put on the right-hand side. The integral of 3x squared is just going to be x cubed, and we will not forget our plus c. And so we've now actually gotten 3 more points here, 1 for this integral, 1 for this integral, and 1 for literally just writing plus c. We can get a 5th point for finding c by plugging in 0 for x and 1/2 for y. So we have 1/2 of e to the 2 times 1/2 is equal to 0 cubed plus c. Or in other words, our constant is just going to be equal to 1/2 of e. Right? Because we have e to the first power there, 1/2 of e is going to be our constant. And so we'll plug that back in here to get 1/2 e to the 2y is equal to x cubed plus 1/2 of e. Now we can, of course, multiply everything by 2 to get e to the 2y is equal to 2x cubed plus e. And then we can take the natural log of both sides to get 2y is equal to the natural log of 2x cubed plus e. And then we can just divide by 2 to get y equals 1/2 the natural log of 2x cubed plus e. And they give you 1 point for finding 1/2 e and plugging it back in, and 1 point here for solving for y to get our final answer. Now that's normally the last part of the differential equation FRQs. For some reason, this time it was the first. So we have 1 more point here, or not 1 more point, but 1 more part, which asks us to find the domain and the range of this function that we just found, right? And our function, I'll rewrite it here. Our function was y equals 1/2 the natural log of 2x cubed plus e. And so we know that when we're looking for our domain here, we know that 2x cubed plus e is going to have to be positive, right? Because we can't take the natural log of a negative, and we also cannot take the natural log of 0. So we know that 2x cubed plus e needs to be positive. And so, well, we can subtract the e and divide by 2 to get x cubed is greater than negative 1/2 of e. And of course, now we can just cube root this. Right? And if x needs to be greater than negative 1/2 of e, then x is going to have to be greater than the cube root of negative 1/2 e. And so we can then just say that our domain is, and you can write it, you could just leave it like this if you wanted to, or you could say the cube root of negative 1/2 e to infinity. That would also be acceptable for your domain. So you got, first of all, 1 point here for just saying 2x cubed plus e is greater than 0. 1 point for the domain, whichever way you chose to write it. And then you're going to get a final point here for the range. And if we take the natural log of things, right, we know that the natural log of things, like logarithmic functions, just go from negative infinity up to infinity, right? They normally have like some vertical asymptote and go from negative infinity to infinity on the range. So we'll note that this was our domain, and then our range should just be negative infinity to infinity, and you get 1 point for that as well. And that is the end of this differential equation FRQ, which was question number 6 from the 2000 AP Calculus AB exam. All right, this is question number 6 from the 2001 AP Calculus AB exam. It's a differential equation FRQ, where we're given a function f that's differentiable for all real numbers. And we know that the point 3, 1/4 is on the graph of y equals f of x. And that the slope at each point xy on the graph is given by this dy dx of y squared times 6 minus 2x. And first, we're asked to just find the second derivative and evaluate it at that point. Well, to take the derivative of y squared times 6 minus 2x, with respect to x, we have to use the product rule. And while doing that, we'll have to use implicit differentiation because we're taking the derivative of a y term with respect to x. So we'll start on our product rule with just the y squared times the derivative of 6 minus 2x, which is just negative 2. And we'll add to it the derivative of y squared, which is 2y dy dx, right? That's implicit differentiation on y squared with respect to x. And then we have to multiply that by 6 minus 2x. And we'll replace our dy dx with y squared times 6 minus 2x, giving us negative 2y squared plus, now we're going to have a 2y times a y squared, that's a 2y cubed. And we're going to have a 6 minus 2x from here and another 6 minus 2x, so that'll be 6 minus 2x squared. And they're going to give you 2 points here just for getting that second derivative correct. And then they're going to give you a third point for evaluating it at the point 3, 1/4. Well, if y is 1/4 and x is 3, right, well, we're going to have negative 2 times 1/4 squared plus 2 times 1/4 cubed times 6 minus 2 times 3 squared, when we replace all the y's with 1/4 and the x's with 3. Well, we'll note right away that 6 minus 6 is 0. 0 squared is still 0, and if I take 0 times anything, I get nothing. So that's all going to cancel out. And now we just have negative 2 times 1/4 squared. Well, negative 2 times 1/16 is negative 1/8. And you get a third point for getting negative 1/8. In part B, it just asks us to solve this differential equation given that same initial condition. And since this is a product of x and y terms, we are going to use a separation of variables to integrate this. So we're going to divide by y squared to get dy over y squared. And we're going to multiply by the dx to get 6 minus 2x dx. And now, well, first of all, they give you a point just for doing that really basic cross multiplication, essentially. So 1 point for separating the variables. And then 1 point for each of the antiderivatives. The integral of y squared, that's the, or dy over y squared is like the integral of y to the negative 2 dy. Right, so we go up to y to the negative 1 and divide by negative 1. So negative y to the negative 1. Right? Or negative 1 over y. Normally we put a plus c, but since there's going to be another constant on this side, having constants on both sides is a little redundant because I could just subtract one from the other and end up with a singular constant on the right. So that's what I'll do. The integral of 6 is 6x. The integral of minus 2x is minus x squared. And of course, we will now add our plus c. So you got 1 point here for this integral, 1 point for this integral, and 1 point for the plus c. And then next is to find the value of c by plugging in 3 for x and 1/4 for y. So we have negative 1 over 1/4 is equal to 6 times 3 minus 3 squared plus c. Well, negative 1 over 1/4 is negative 4. And 18 minus 9 is 9. So we have negative 4 equals 9 plus c, or c is negative 13. And we'll plug that in here, giving us negative 1 over y is equal to 6x minus x squared minus 13. And you get another point for just doing that, for finding the c and plugging it in. And you'll get a 6th point for correctly solving for y. So first I'll just multiply everything by a negative 1. So I'm going to have 1 over y equals, that's going to give me a positive x squared, a negative 6x, and a positive 13. And then we'll just take a reciprocal, giving us y equals 1 over x squared minus 6x plus 13. That's your 6th point for part B. And that is the end of this differential equation FRQ, which was question number 6 from the 2001 AP Calculus AB exam. All right, this is question number 5 from the 2002 Form B AP Calculus AB exam. It's a differential equation FRQ. And in the first part here, it says, let y equals f of x be the particular solution to the differential equation above. 3 minus x over y is equal to dy dx. On the interval 1 to 5, such that the line y equals negative 2 is tangent to the graph of f. First, find the x coordinate to the point of tangency, and then determine whether f has a local max, min, or neither at that point. So, if a horizontal line is tangent, that means that dy dx must be equal to 0, because the slope of a horizontal line is 0. Well, that's equal to 0 if x is equal to 3. So to start off with, we know that this happens when x is equal to 3. So then we need a second derivative to determine if it's a max, a min, or neither. So our second derivative we'll take using implicit differentiation and the quotient rule. So we start with the denominator, y, times the derivative of the numerator, which is negative 1, and then minus the numerator times the derivative of the denominator, which is dy dx, all divided by the denominator squared. And when we evaluate this at x equals 3 and y equals negative 2, because that's our y value, and we also know that dy dx has got to be equal to 0, right, at this point. So that means that we can just eliminate this whole second portion of our numerator. We really just have negative y, or 2, over negative 2 squared, which gives us 1/2. Well, 1/2 is positive. And so if the second derivative is positive, then we know that this should be concave up. We'll say that f is concave up, and it has a minimum at that point. So you got 3 points here, one for finding x equals 3, one for saying it was a minimum, and one for your justification that our second derivative was positive there. And here in part B, we've now got y equals g of x as a particular solution to this. For negative 2 to 8, and the initial condition is g of 6 is negative 4. We want to find g of x. So really all we're doing here is doing a separable differential equation. So it's we just bring the y to the other side by multiplying y dy equals 3 minus x dx. And they gave you 1 point, of course, as always, just for separating the variables. And this year they were exceptionally generous. If you integrated both sides correctly, which are both very easy integrals, just the power rule there, then you ended up getting a point for each integral and a point for having the plus c. Then you need to solve for c. So plug in your initial condition that when x is 6, y is -4. So we have -4 squared over 2 is equal to 3 times 6 minus 6 squared over 2 plus our constant. So 8 equals 18 minus, well, 36 over 2 is also 18 plus our c. So our constant is 8. Plugging that back in here gives us y squared over 2 equals 3x minus x squared over 2 plus 8. We get a point for having the constant and plugging it in. And we'll get our final point for solving for y. So first we'll multiply by 2. 6x minus x squared plus 16. And then we square root. And when we square root, we need to make sure that we get a plus or a minus here to start with. But then a small bit of analysis sees that our y value needs to be -4. And if I put a positive outside that square root, my y value cannot be -4. So I need to have a negative sign out in front of that square root. So this is our final answer. That's the 6th point for part B. And that is the end of this differential equation FRQ number 5 from the 2002 Form B AP Calculus AB exam. All right, this is question number 5 from the 2003 AP Calculus AB exam. It is a differential equation FRQ, and we're given a coffee pot in the shape of a cylinder with a radius of 5 inches. And h is the depth of the coffee in the pot in inches, and it's a function of time measured in seconds. It tells us that the volume of the coffee in the pot is changing at this rate, -5 pi root h. And it tells us volume is pi r squared h. It then says, show that dh dt is -root h over 5. Well, if the volume is equal to pi r squared, I don't know why I have to underline that, pi r squared h, then dv dt should be able to be found using the product rule and implicit differentiation. That'll be pi r squared times the derivative of h with respect to t, plus the derivative of pi r squared, which is 2 pi r dr dt, times the h. And you don't really need to worry about the second part of this here, right? Because dr dt, and you could have already plugged in your r if you wanted to and not done this, but dr dt is equal to 0, which means this whole term just goes away. So you really could have started with volume is 25 pi h if you wanted to, right? And now when we plug in our dv dt, which we know dv dt is given as -5 pi root h, that should equal pi times our radius of 5 squared times dh dt. And then if we just solve for dh dt, well, we could cancel out the pi's. And if we do -5 over 25, that's -1/5. So it's -root h over 5, which is exactly what we were supposed to show that it was equal to. And they gave you 3 points for that. 1 for eventually getting down to this dv dt is negative, or using dv dt equals -5 pi root h in there. 1 for actually finding what dv dt was, so like doing this or getting this, either one would be fine, and 1 for simplifying it down and showing the result. In part B, it asks us to solve the differential equation dh dt equals -root h over 5, given that h is 17 when t is 0. So we got to separate the variables first because this is a separable differential equation. So we'll do dh over root h is equal to negative 1/5 dt. Right, we're just bringing the dt to the right and the root h to the left. They're going to give you 1 point just for separating the variables. And then you're going to integrate both sides here. And they're going to just give you 1 point this time for the integrals. Negative 1/5 t plus your constant on the right. And then on the left, the integral of 1 over root h, that's h to the negative 1/2. So we go up to h to the 1/2, or root h, and we divide by 1/2, which is the same as multiplying by 2. So we get 1 point there for doing the antiderivatives, plus 1 point for just having the plus c. Then you need to solve for c. So you're going to put in 17 for h and 0 for t. So 2 root 17 equals 0 plus c, or that's our constant. So now we can go back in and we can plug in 2 root 17 into 2 root h equals negative 1/5 plus 2 root 17. And we'll just, negative 1/5 t plus 2 root 17. We'll divide by 2, and then we'll square. So we get root h is equal to negative 1/10 t plus root 17. And then we'll just square it to get h equals negative 1/10 t plus root 17, all squared. And that was worth 5 points. So we already talked about the first 3. The fourth one was for actually finding c and plugging it in. And the fifth one is for getting your final answer. And part C asks us, at what time t is the coffee pot empty? Well, that would be when h is equal to 0. And we just got a function for h right here. So we just need to set that equal to 0. Negative 1/10 of t plus root 17 all squared needs to equal 0. Well, the squared part doesn't really matter. Right? We can square root both sides. Now we just have negative 1/10 t plus root 17 equals 0. And we can solve for t. We'll add the 1/10 t over and then multiply by 10. T is 10 root 17. And you got 1 more point for getting that final answer. And that is the end of this differential equation FRQ, which was question number 5 from the 2003 AP Calculus AB exam. All right, this is question number 6 from the 2003 Form B AP Calculus AB exam. This is a differential equation FRQ. And it starts by giving us f prime of x, which is x root f of x. And it says it is valid for all real numbers x, where f of 3 is 25. And we want to find f double prime of 3. So we're going to get a second derivative here. We're just going to take the derivative of x root f of x. So f double prime of x, we'll use the product rule, right? It's x times the derivative of root f of x. Well, root f of x has a derivative of 1 over 2 root the function times the derivative of the function, which is f prime of x. Then we'll add to that with the product rule, the second part of the product rule, the derivative of x, which is 1, times root f of x. And so now, in order to figure out what this is equal to at 3, we'll just need to use that information that f of 3 is equal to 25. And we need to find what f prime is equal to, but we can note that f prime, right, is equal to x root f of x. So really what I've got here now is an x squared times a root f of x in the numerator over 2 root f of x in the denominator plus a root f of x. And of course I can cancel these root f of x's to just get x squared over 2 plus root f of x. And that'll make my life a little bit easier on my evaluation. So now f double prime of 3 is just going to be 3 squared over 2 plus the square root of f of 3. Well, f of 3 is 25. So we end up with 9 halves plus 5. Well, 5 is 10 halves. So add those together and you get 19 halves. And you got 3 points here for part A. 2 actually, for correctly getting f double prime of x, and 1 more for the final answer. And part B asks us to write an expression for y equals f of x by solving this differential equation dy dx equals x root y, given that same initial condition. So dy dx equals x root y is a separable differential equation. So we're just going to start by dividing by root y and multiplying by dx. So we get dy over root y equals x dx. And of course, you get 1 point just for separating the variables. Then you're going to integrate. And of course, the integral of x is just x squared over 2. So that one's pretty straightforward. Don't forget your plus c. And the integral of root y, well, that's an integral of y to the negative 1/2. So we go up to y to the 1/2, or root y, and divide by 1/2, which is the same as multiplying by 2. So we have 2 root y equals x squared over 2 plus c. And we don't need to put a constant on the left-hand side, because a constant on each side, we could just subtract one from the other and end up with a singular constant on one side. So now we're going to, we get the points for this. 1 point for each antiderivative, and 1 point for just putting your plus c. And then now we'll plug in x equals 3 and y equals 25. So we have 2 root 25 equals 3 squared over 2 plus c. But 2 root 25 is 10. So 10 equals 9/2 plus c, which gives us c is equal to 11/2. And we'll then plug that back into our 2 root y equals x squared over 2 plus c, so plus 11/2. We'll divide everything by 2, and when we do that, we can, of course, just put this into a singular fraction. X squared plus 11 over 2 divided by 2 more is going to be 4. And then we'll just square both sides. So y is equal to x squared plus 11 over 4 squared. And that should be our final answer. You got 1 more point here for using the initial condition and getting 11/2, and 1 more point for the final answer. And that is it for this differential equation FRQ, question number 6 from the 2003 Form B AP Calculus AB exam. All right, this is question number 6 from the 2004 AP Calculus AB exam. It's a differential equation FRQ. And they ask us first to just sketch the slope field for the differential equation dy dx equals x squared times y minus 1 at the 12 points that they give us here. So the first thing we'll note is that if x is equal to 0 or y is equal to 1, then dy dx must be 0, right? Because if x is 0, we have 0 times y minus 1, which is 0. And if y is 1, then we have x squared times 0, which is also 0. So everywhere when y is 1, or when x is 0, we have slopes of 0. And that takes care of 6 of the points. And so now we just need to do the other 6. So let's start with 1, 0. If I do 1, 0, and plug that in, we have 1 squared is 1, and times 0 minus 1. 0 minus 1 is negative 1. So we get negative 1 here. And we'll note, that looked a little too steep. Let me make that a little less steep. It's maybe a little better. Negative 1. That looks a little too shallow. Let's try and do better this time. Oh, that's perfect. And then if we think about this, since we're squaring the x value, but the y is not changing here, if I move over to negative 1, 0, there's no difference between 1 and negative 1 if I square, right? It's just 1 either way. So we'll note that anything over here in this column is going to be identical to what I see in this column, right? Because the y's are staying the same, and the x's, once it's squared, is the same value on both sides. So this at negative 1 is also going to be negative 1. Then we'll do the point 1, 2. And we'll mirror it over as the point -1, 2 also. So 1, 2 just gives us 1. So there are our slopes of 1. And then if we do the point 1, 3, well, that should give us 1 times 2. So we've got a little bit steeper over here. And we'll mirror it. And we get 1 point for all the 0 slopes here. And we got 1 for all the other slopes. In part B, it asks us for all points in the xy plane for which the slopes are positive. Well, we know that x squared is always positive. So really we just need to look at when is y minus 1 positive. In fact, we know x squared is always positive or 0, right? X squared is always greater than or equal to 0. And so this is true when y is greater than 1. So anytime y is greater than 1, we should have positive slopes, except if x was equal to 0. So we need to also clarify that y is greater than 1, but x is not 0, because if x is 0, we end up with 0 as our slope. So any point where y is greater than 1 with x not equal to 0. And you got 1 point for that. And then here in part C, you are asked to solve the differential equation with the initial condition that f of 0 is 3. And this is, of course, a separable differential equation because it's dy dx equals a product of x and y. So we'll first separate the variables by dividing by y minus 1 and bringing the dx to the other side. That's worth 1 point just by doing that. Then you can integrate both sides here. And the integral of x squared is just x cubed over 3 plus a constant. And for dy over y minus 1, we do the basic u sub, that u is y minus 1, and du is dy. So the integral is really just an integral of du over u. So it's natural log absolute value of u, which is y minus 1. We don't really add the plus c on the left side, because if we have a constant on the left and a constant on the right, I could just move that constant from the left to the right and end up with a singular constant on the right-hand side. Now, we'll give ourselves our points here. We actually got 3 points here. 1 for this antiderivative, 1 for this antiderivative, and 1 for just writing plus c. You can get your next point by solving for the constant using your initial condition that when x is 0, y is 3. So that gives us natural log 2 equals 0 plus c, or a constant of ln 2. We'll plug that back in, giving us the natural log of the absolute value of y minus 1 is equal to x cubed over 3 plus the natural log of 2. And now we get another point just for doing that. And now we just solve for y. So whenever we have natural log of something with y, we want to exponentiate. That gives us absolute value y minus 1 equals e to the x cubed over 3 times e to the ln 2. Remembering that e to the a plus b is equal to e to the a times e to the b. So the reason we want to do that is because e to the ln 2 is just 2. So now we have 2e to the x cubed over 3. And to clear out the absolute value from the y minus 1, we throw a plus or minus out in front. And when we do that, we immediately want to go back to our initial condition, that when y is 3, so we're going to look over here. When y is 3, we get 3 minus 1 equals positive or negative 2e to the 0. Well, we need to get 2 equals positive or negative 2. So clearly we need to choose the positive thing. And I don't need to put a plus in front. We just will make sure we don't put a negative. We'll add 1 to the other side, giving us y equals 1 plus 2e to the x cubed over 3 as our final answer. That gives us the 6th point for part C, and that's the end of this differential equation FRQ, which was number 6 from the 2004 AP Calculus AB exam. All right, this is question number 5 from the 2004 Form B AP Calculus AB exam. This is a differential equation FRQ. We're given dy dx equals x to the 4th times y minus 2. And to start with, they just want us to sketch the slope field at the 12 indicated points. So we'll note that anywhere where x equals 0 or y equals 2, dy dx will be 0, right? Because if x is 0, we get 0 times y minus 2. And if y is 2, we get x to the 4th times 0. Both of those will just always be 0. So when y is 2, we got 0. And when x is 0, we've got 0. So that takes care of 6 of the 12 points right off the bat. That's pretty straightforward. And then we'll just find the last 6, just plug in some points. If I put in the point 1, 0, well, that's going to be 1 times negative 2. So that'll be negative 2. We make a slope of negative 2 there. And if I put in the point negative 1, 0, we're also going to get a slope of negative 2, right? Because negative 1 to the 4th is still going to be positive 1. In fact, we'll note that when we find the point in the first quadrant, the point in the second quadrant should be mirrored because 1 to the 4th and negative 1 to the 4th are the same thing. So the point 1, comma 1, right, should give us 1 times negative 1, or just negative 1. And of course, as we just said, over here in the third quadrant, or second quadrant, it should be exactly the same. And then for the point at 1, 3, we should get 1 times 1, which is just 1. And we'll mirror that again over here in the second quadrant. And that is your slope field. They gave you 2 points. So one of those was for the 0 slopes, all the slopes of 0. Right, so these ones, that was 1 point. And then they gave you 1 point for all the rest of them. In part B, it says, we drew that slope field at 12 points, but it's defined for every point in the xy plane. Describe all points in the xy plane for which these slopes are negative. Well, when can x to the 4th times y minus 2 be less than 0? Well, it's only going to be less than 0 if y minus 2 is less than 0. Because x to the 4th is always either 0 or positive. And so y minus 2 is less than 0 if y is less than 2. So any point in which y is less than 2, and of course we can't have x equal to 0 because then we would have it equal to 0. So if y is less than 2 and x is not 0, that's when the slopes are negative, and they gave you 1 point for part B. In part C, we want to find the particular solution, y equals f of x, to this differential equation, given the initial condition of when x is 0, y is 0. So this is a separable differential equation, so we'll start by just separating the variables. Dy over y minus 2, we'll divide by the y minus 2, and then we'll bring the dx to the other side, so x to the 4th dx. And we'll integrate. You get 1 point just for separating them. And you're going to get 1 point for each antiderivative. On the right-hand side, that's just x to the 5th over 5 plus your constant. And on the left-hand side, that's a basic u sub, where u is y minus 2, so du is dy. So it just is an integral of du over u, which we should know is natural log absolute value of u, and our u is y minus 2. And we don't need to put the constant there because having constants on both sides is kind of redundant. If we had them on both sides, we could subtract 1 to the other and just have a constant on one side. So we're just gonna do that. Leave it with the plus c only on the right-hand side. And they'll give you, for this problem, 1 point for this integral, 1 point for this integral, and back in 2004, they used to give you 1 point just for writing plus c. Pretty generous. Now we're going to plug in 0, 0. So we get the natural log of the absolute value of negative 2 is 0 plus c, or our constant is ln of 2. We'll take that and plug it in here. So what we get is the natural log of the absolute value of y minus 2 is equal to x to the 5th over 5 plus that constant ln 2. You get another point just for finding that c and plugging it in. And then you'll get your last point if you actually successfully solve for y. So we'll exponentiate both sides to get absolute value y minus 2 is equal to e to the x to the 5th over 5 times e to the ln 2. Remember, exponent rules say e to the a plus b is equal to e to the a times e to the b. And the reason we do that is so that we can turn e to the ln of 2 into just a 2 out in front there. So now we have 2e to the x to the 5th over 5. And we're going to clear off that absolute value by putting a plus or a minus in front. And when we do that, we immediately want to check and see which one do we want. Well, the one we want is the one that makes our initial condition still true, 0, 0. So I'm going to write this off to the side over here. Using this, right, we have 0 minus 2 equals plus or minus 2e to the 0. Well, 2e to the 0 is 2. So I want to have negative 2 equals either plus or minus 2. Well, clearly, it has to be the minus. So we'll go in here and erase the plus and just take the negative on that 2e to the x to the 5th over 5. Now we'll just add our 2 over. So we have 2 minus 2e to the x to the 5th over 5. That's our final answer. That's the final point of part C here on this differential equation FRQ, which is 2004 Form B, problem number 5 from the AP Calculus AB exam. All right, this is question number 6 from the 2005 AP Calculus AB exam. This is a differential equation FRQ. And in part A, they just want us to sketch a slope field at the 12 indicated points. And so we'll note, first of all, that dy dx, and this is always a good place to start, dy dx is 0 if x is 0, given our differential equation that dy dx is negative 2x over y, right? If x is 0, we're going to get 0 as long as y is not 0. And we don't have any points when y is 0 on the x-axis, so we don't have to worry about that. So anywhere where x is 0, we're going to put a slope of 0. And now we just have 8 more points to do. And whenever it's just a negative 2x over y, right? Whenever it's just no addition or subtraction in there, just a multiplication or a division of x and y, each quadrant will just be a reflection of the other ones next to it. So if I just figure out what it is at 1, 1 and 1, 2, I can just reflect those down or over into all the other quadrants. So at 1, 1, when we plug that in, we end up getting negative 2 over 1. So just negative 2, which means I can reflect that down to the 4th quadrant with a slope of positive 2, and also over into the 2nd quadrant with the slope of positive 2. And I can reflect those down into the 3rd quadrant with a slope of negative 2. And then on 1, 2, if we plug in 1, 2 for this one, if x is 1 and y is 2, we end up getting negative 1. So we'll put a slope of negative 1 there, and that'll reflect to all the other quadrants as a positive 1 in the 4th and in the 2nd quadrants, and a negative 1 in the 3rd quadrant. And they gave you 2 points for that, 1 for the 0 slopes and 1 for all of the other slopes. And then here in part B, they just ask us to write an equation for the tangent line to f at the point 1, 1, or 1, negative 1, and then approximate f of 1.1 using that tangent line. So to write the equation of a tangent line, we just need a point and a slope. Our point is just given to us. It's the point 1, negative 1. And then the slope of the tangent line comes from its derivative. And since we're looking for a tangent line to the solution to this differential equation, its derivative is just the differential equation. So we're going to evaluate dy dx at the point 1, negative 1. So we'll get negative 2 times 1 for x divided by negative 1 for y, which gives us positive 2. So the equation of our line is just going to be in point slope form. Y plus 1 equals 2 times x minus 1. And they gave you 1 point just for finding that equation. And then they give you another point for plugging in 1.1 and solving for y. So y plus 1 equals 2 times 1.1 minus 1, or y plus 1 equals 0.2. So y is negative 0.8. And that's the second point there in part B. And the last part of this FRQ is part C, where it asks you to find the particular solution given that same initial condition. And so we'll note that this is a separable differential equation because it's a product or quotient of x and y. So step 1 is just to separate the variables, bring the y over to the left side with the dy, and bring the dx over to the right side with the negative 2x. And they're going to give you 1 point just for separating the variables. Then you need to integrate both sides. Those are both pretty straightforward integrals. So our first one is y squared over 2. And our other one, negative 2x, just becomes negative 2x squared over 2, or negative x squared. And of course, don't forget the plus c. You could have a constant on the left side as well, but if you subtract that constant from the left over to the right, you're just left with a singular constant on the right-hand side again. So normally we just put it on the right-hand side. They gave you 1 point for having the antiderivatives correct, and 1 point for putting plus c. And then the next point is for solving for c with your initial condition, that when x is 1, y is negative 1. So we've got negative 1 squared over 2 equals negative 1 squared plus c. Well, negative 1 squared is 1, so we have 1/2 equals negative 1 plus c, or a constant of 3/2. And if you take that constant of 3/2, plug it back in for c, and rewrite as y squared over 2 equals negative x squared plus 3/2, you get another point. So that'll be the fourth point for this one. And then solving for y gives you the fifth point. So we'll start off by multiplying everything by 2. So that gives us negative 2x squared plus 3. And then we square root. And when we square root, we get plus or minus the square root of negative 2x squared plus 3. But we can't pick both of those. We have to go back again to our initial condition that when x is 1, y needs to be negative 1. So if we say negative 1 equals plus or minus the square root of negative 2 times 1 squared plus 3, well, clearly we can't have negative 1 equals a positive square root. We need to have negative 1 equals the negative square root. So we'll get rid of the plus sign there. And our final answer should be y equals negative square root of negative 2x squared plus 3. And that is the last point for that, for this differential equation FRQ, which was question number 6 from the 2005 AP Calculus AB exam. All right, this is question number 6 from the 2005 Form B AP Calculus AB exam. This is a differential equation FRQ, where they've given us a differential equation. dy dx is negative xy squared over 2. It's a separable differential equation because it's a product of x and y. And we've got an initial condition that f of negative 1 is 2 for our solution, y equals f of x. So first it just wants us to draw a slope field here at these 12 points. This should be a really easy slope field because we'll note that if x equals 0 or y equals 0, then dy dx must be 0, right? If I take 0 times y squared over 2 and put a negative in front, it's still 0. Or negative x over 2 times 0 squared is 0. So anywhere where x or y is 0, we should have a slope of 0. So anywhere on the x or the y axis, we should have slopes of 0. And they gave you 1 point, actually, for doing that. And then they gave you another point for having the rest of them correct. We'll just plug in values. So let's say we start with 1, 1. If I plug in 1, 1, we get negative 1/2 when we plug x and y in as 1. So we'll draw a slope of negative 1/2 there. If I put in the point 1, 2, if x is 1, that's negative 1. And then if y is 2, that's 4 up there. So negative 4/2 is going to be negative 2. So we're going to get kind of steep there, negative 2. If we do the point 2, 1, plug in 2 for x and 1 for y, we get negative 1, right? Negative 2/2. So just make sure that's kind of between your negative 1/2 and your negative 2 slopes. And then at 2, 2, we're going to get negative 2 times 2 squared. So negative 2 times 4 is 8, or negative 8, over 2, which is negative 4. So we're just going to get a really steep slope there. So just make sure that one's steeper than the one that you had at the point 1, 2. Then we got 2 more to do on the other side. If we put in negative 1, 1, negative 1 for x makes negative x a positive 1. And then we do 1 squared is 1/2, just gives us 1/2. So make that about the same as the negative 1/2, but flipped. And then at negative 1, 2, we're going to put in negative 1 for x again. So that's just a 1. And then 2 squared is 4. 4/2 is 2. So just make that about the same as the one that was a slope of negative 2 on the other side. And they gave you 1 point for all the rest of the slopes there. In part B, it says write an equation for the line tangent to the graph of f at x equals negative 1. Well, we've already got the point, negative 1, 2. We just need the slope. And the slope of a tangent line to f should come from its derivative, which is negative x y squared. So we'll evaluate dy dx at the point negative 1, 2, which we actually just did a second ago, but we'll write it out this time. It's negative 1 times 2 squared over 2, which negative 1 is 1, 2 squared is 4, and 4 divided by 2 is 2. So our equation is just in point slope form. Y minus our y value of 2 equals 2 times x minus negative 1, or x plus 1. And it's perfectly acceptable to just leave it in this form. They just gave you 1 point here in part B for getting that equation. And now in part C, we're going to get our last 6 points here to solve the differential equation with the given initial condition. And so this is a separable differential equation, so we're going to bring all the y stuff to the left and the dx to the right. So we're going to have dy over y squared equals, or if we divide by the y squared, equals negative x over 2 dx, bringing the dx to the right. And you get 1 point just for doing that, for separating. And then we're going to integrate both sides. And so the integral on the right is just going to be negative x squared over 4 plus a constant. And the integral on the left, well, don't make the mistake of saying natural log absolute value y squared. That's a common mistake. This is just an integral of y to the negative 2 dy. So just integrate using the power rule, go up to y to the negative 1 and divide by negative 1. So it's negative y to the negative 1, or negative 1 over y. And I don't put the plus c on the left, because if I had a plus c and another constant on the right, if I had one constant on the left and one on the right, I could subtract the one on the left over to the one on the right, and a constant minus a constant is some other constant. So not really necessary. They gave you 1 point for each of these antiderivatives and 1 point for putting plus c. You get a 5th point if you solve for c and plug it back in correctly. So when x is negative 1, y is 2. So negative 1 over 2, because y is 2. And if x is negative 1 squared is 1. So we have negative 1 over 4 plus c. So just add your 1/4 over there, and you get c is negative 1/4. We'll plug that in, and what does that give us? Negative 1 over y equals negative x squared over 4 minus 1/4. And that's a 5th point here, just for getting that c and plugging it in. if I multiply both sides by -1, we get 1 over y on the left, and on the right, we get a positive x squared and a positive 1. And since they're both over 4, we'll just combine it into one fraction. Now we just have to take our reciprocal here of both sides to get y equals 4 over x squared plus 1, which is the final answer, and the 6th point there for part C, and the 9th point on this differential equation FRQ, which was question number 6 from the 2005 Form B AP Calculus AB exam. All right, this is question number 5 from the 2006 AP Calculus AB exam. This is a differential equation FRQ. We've been provided with the separable differential equation dy dx equals 1 plus y over x, where x does not equal 0. And they just ask us first in part A to sketch the slope field of this at the 8 indicated points. And so we're going to first note that what makes this equal to 0 is when we have y equal to -1. So if y equals -1, dy dx is 0. So that'll be at these 2 points down here. And then now we just have 6 points remaining. And so we'll just plug in each of those to see what the slopes are. At the point 1, 0, if we put in 1 for x, right, the denominator is just going to go away. So we'll just have 0 plus 1 up there. So that one's 1. So at 1, 0, it should be 1. Then we'll do 1, 1. And again, the denominator is just going to be 1. So we end up with 1 plus 1 in the numerator, which is 2. So we'll just make it a little steeper. And then at the point 2, comma 0, the denominator is going to be 2. We're going to have 1 plus 0, which is 1, over 2. So, a slope of about a half there. Then we'll flip over to the negative side there. If we put in -1, 0, we're going to have 1 over -1, which is -1. And we'll see that all that's happening here is we're getting the same values with the y's, but the x's are just turning negative. So we've got -1 there, and then the one at -2, 0 should just be -1/2. And then the one at -1, 1 should just be -2. And that is our slope field. They gave you 2 points for the slope field, right? Noting that when the x values change from positives on the right of the y-axis to negatives, all that's happening is we're flipping the sign of each of the things. So it's just a mirror image over that y-axis. And this is a really short differential equation question. This is our last part of the question. It's just asked us to solve this with the initial condition that f of -1 is 1, and then to state the domain. So first off, this is a separable differential equation because it's a product of a function of x and a function of y, or a quotient, right, in this case. So we're just going to separate the variables. We'll divide by 1 plus y on both sides to get dy over 1 plus y. And then we'll multiply by the dx to just get dx over x. And they give you 1 point here just for separating the variables. Then we need to integrate both sides. On the right-hand side, it's natural log absolute value of x plus a constant. And on the left side, it's going to be natural log absolute value of 1 plus y. And of course, we could add a constant there, but if I had a constant there, I could just subtract it over to the other side, have 2 constants on the right. Well, a constant and another constant just make a constant, so perfectly fine to just have the constant on the right only. And note that this is a basic use of, right, u is equal to 1 plus y, and du is just dy. So really, it's just an integral of du over u, which is natural log absolute value u, or natural log absolute value, in this case, of 1 plus y. They gave you 1 point for each of these antiderivatives, and they even gave you 1 point for just writing plus c. Then they give you a 5th point if you use your initial condition, f of -1 equals 1, to actually find the value of c. So y is 1, gives us natural log of 2. And then if x is -1, the absolute value of -1 is 1, so we get natural log of 1 plus a constant. Well, we know that the natural log of 1 is 0, so we just get the constant is ln of 2. So we'll just plug that back in up here to get our next point. Natural log absolute value 1 plus y is equal to natural log absolute value of x plus the natural log of 2. And so we get one more point there. And then we just need to solve for y and state the domain. So as we solve for y, we're just going to exponentiate both sides, or we're going to raise as powers of e. And that gives us absolute value 1 plus y is going to be equal to, well, e to the a plus b. Right? We know that e to the a plus b is the same as e to the a times e to the b. So this is e to the natural log absolute value of x times e to the natural log of 2. Well, we know that e to the ln of anything is just the thing. So really what we end up with here is the absolute value of 1 plus y is equal to 2 absolute value of x. And so what we'll do here is we'll just clear off our absolute values. Right, so we're going to get 1 plus y is equal to plus or minus 2 absolute value of x. And now we want to decide if we want the positive or the negative value here. So again, we'll go back to our initial condition that when x is negative 1, y needs to be 1. So we'll test that off to the side here. 1 plus 1 equals plus or minus 2 times the absolute value of negative 1, which is just 2 times 1. Well, 1 plus 1 is 2, not negative 2, right? So we want the positive value here, which means I'm not going to have a plus or a minus. I'm just going to have 1 plus y equals 2 absolute value x, or y is equal to 2 absolute value of x minus 1. This answer is good. We're going to look at what another form of it could look like in a second when we worry about the domain. Right? So it asks us to state the domain, and when we look for the domain, or the interval on which a solution to a differential equation is valid, we have to take into account any restrictions that come out along the way. And so we'll note over here that as soon as we took the antiderivative of dx over x, we knew that x could not be 0. We could have any other value for x, and that restriction has to hold all the way to the end, which means that the domain overall that we'd be looking at would be negative infinity to 0 and 0 to infinity. But when we state the interval of validity, or the domain for these, we pick the single continuous piece, so we can't pick both pieces, the single continuous piece that includes our initial condition of x equals negative 1. Well, x equals negative 1 falls between negative infinity and 0. So we're going to say for negative infinity to 0, and that'll be our domain. And so this answer is perfectly fine, and that'll earn you the 5th point for the function and the 6th point for, or sorry, the 6th and the 7th points for your function and your domain for this problem. But you could also note that since x is always negative here, right, x is always going to be negative on negative infinity to 0, well, if x is less than 0, the absolute value of x is the opposite of x. So we could use y equals negative 2x minus 1. This would also be an acceptable answer here for negative infinity to 0, or you could say for x less than 0. So either way you choose to write it is good. And that is the end here of this differential equation FRQ. It was question number 5 from the 2006 AP Calculus AB exam. All right, this is question number 5 from the 2006 Form B AP Calculus AB exam. It's a differential equation FRQ where they've given us a separable differential equation, dy dx is equal to y minus 1 squared times the cosine of pi x. And then they ask us to, first off, sketch a slope field here. And so in order to sketch this slope field, the easiest thing to do to start with is to recognize that if y equals 1, then dy dx must be 0. So that means everywhere where y is 1, we should just draw a slope of 0. That only now leaves us with 6 points to test. And so we'll do that for each of those points. We'll just start at the origin. If we put in 0, 0, 0 minus 1 squared is 1. So we end up with 1 times the cosine of 0 times pi, or the cosine of 0. So we just get 1 times 1, which is 1. If we put in the point 1, 0, if x is 1, we're taking the cosine of pi. And the cosine of pi is negative 1, and we're going to multiply that by 1. So that's going to give us negative 1. And if we do negative 1, 0, the same thing is going to happen. We have the cosine of negative pi times 1, which is also negative 1. So both 1, 0 and negative 1, 0 have a slope of negative 1. Then moving down here to when y is negative 1. So when y is negative 1, we're going to have negative 1 minus 1 squared. So that's negative 2 squared, or 4. So we're just going to get 4 times either the cosine of pi, the cosine of 0, or the cosine of negative pi. Well, we're going to get then negative 4, 4, and negative 4 for each of those respectively. Right? So the first one was at 1, negative 1. So that one's going to be negative 4, then positive 4, then negative 4. And they gave you 2 points for this, 1 for the ones that were 0 and 1 for all the other ones. So 2 points there for part A. In part B, it says there is a horizontal line with equation y equals c that satisfies this differential equation. There's not really any work here to do to find the value of c. If we just think about what we just did, right? Well, what we just did is that we showed that if y is 1, we get a horizontal line. Right? If we're on the line y equals 1, the slopes are always 0. And therefore, you can't get off that line. So that must be y equals 1, right? C is 1. And so that is our singular point there for part B. And we can see that, we saw that in the slope field. So not too bad. Now part C, we're going to find the particular solution to this differential equation with the initial condition that f of 1 is 0. So since we only got 3 points from parts A and B, this is 6 points for part C. And again, it's a separable differential equation, so we're going to start by separating the variables. Dy over y minus 1 squared, so we're dividing by y minus 1 squared, is equal to cosine pi x times dx. We're bringing the dx to the right-hand side. And you got 1 point just for correctly separating the variables. You're going to get a couple points for the antiderivatives here for correctly doing each of these, because they both require a u sub. And so if u is y minus 1, then du is just dy. And so this integral looks like the integral of du over u squared, or u to the negative 2 du. Well, the integral of u to the negative 2 is just negative 1 over u, or negative 1 over y minus 1. And of course, we'd add a plus c, but since we're going to have a plus c on the other side, we don't need to put it on both sides. So for this one, the substitution, we'll use v this time. V is going to equal pi x. So dv will be pi dx, which means I really need to add in a pi inside of here with a 1 over pi outside. So now it's pi times the cosine of pi x dx, which is just 1 over pi times the integral of cosine v dv. Well, the integral of cosine is sine, so what we've got is 1 over pi sine of v, or sine of pi x, plus a constant. And so actually all the work we've just done right now gives us 3 more points. 1 for this integral, 1 for this integral, and 1 literally for just writing plus c. The next step is to find the value of c. So we're going to use our initial condition that f of 1 is 0. So when x is 0, or when x is 1, y is 0. So negative 1 over 0 minus 1 needs to equal 1 over pi times the sine of pi plus our constant. Well, negative 1 over negative 1 is just 1, so we get 1 equals the sine of pi is just 0, right? So we just get 1 equals c here. And so now all we'll do is we'll put that c equals 1 back in, and we will solve for y. So we now have negative 1 over y minus 1 equals 1 over pi sine pi x plus 1. And so we'll get rid of the negative sign here. So there's a couple options on how to get rid of that negative sign. I'm just going to say we now have 1 over y minus 1 is equal to the opposite of 1 over pi sine pi x plus 1 to start with. And then we need to now take a reciprocal of both sides. Well, that's going to give us y minus 1 equals, I'm just going to put a negative here, and then I'm still going to take the reciprocal 1 over pi sine pi x plus 1. And then we'll just add 1 to this. So we'll get y equals 1 minus 1 over pi sine pi x plus 1. And if you want to, of course, you can just, you can multiply both the top and the bottom by pi if you prefer to get rid of the 1 over pi. So it would look like pi, or 1 minus pi over sine pi x plus pi. And either of these answers would be perfectly acceptable. And so we got our 5th point here for just getting that c value, and our 6th point here for our final answer. And that is the end of this differential equation FRQ, question number 5 from the 2006 Form B AP Calculus AB exam. All right, this is question number 5 from the 2007 Form B AP Calculus AB exam. It's a differential equation. It's a little bit different of a differential equation problem, where we have dy dx equals 1/2 x plus y minus 1, where it's not a product of x and y. So it's not a separable differential equation like they normally are. But that's okay. We should still be able to get through it. No problem. First, we just want to sketch the slope field at these 9 different points. So all you really need to do is just test each of these values. We'll start with the easiest one at the origin at 0, 0. Right? If we plug in 0 for x and y, we just get -1. So we'll start with the slope of -1. If we go up to 0 for x, 1 for y, right? 0, 1, we're just going to get 0, right? 0 plus 1 minus 1, so make sure you have a nice horizontal slope there. And then at 0, 2, right, we're going to have 0 plus 2 minus 1, which is just 1, so a slope of 1. For all the ones at 1, so at 1, 0, we're going to start off with a half. So we're always going to have a half plus the y value. So in this case, it's a half plus 0, and then minus 1, which is negative a half. So it should be negative, but less steep than the -1 that we had. When we do 1, 1, we're going to have a half plus 1 minus 1, which is a half. So a half. And then when we have 1, 2, we're going to have a half plus 2 minus 1. So a half plus 2 would be 5 halves minus 1 would be 3 halves. So we should be steeper than it is at 1. So there we go, 3 halves. And then when we do -1, 0, and if we plug in -1 for x, we're getting -1/2. So we have -1/2 plus 0 minus a half is -3 halves. So this one should be about as steep as the other one was for 3/2, just in the opposite direction. When we do negative 1, 1, we'll have negative 1/2 plus 1 minus 1. So that's just going to be negative 1/2. So that one's going to be, not very steep at all. And then when we do negative 1, 2, we'll have negative 1/2 plus 2 minus 1, which is going to be positive 1/2. So it'll look about like that. And they just gave you 2 points for having the slope field completed, looking just about like that in part A. In part B, it asks us to find the second derivative in terms of x and y, and then describe some stuff about solution curves for it. So we'll find the second derivative first. Remember that we're doing a derivative with respect to x of our differential equation. So the derivative of 1/2 x with respect to x is 1/2. The derivative of y with respect to x is dy dx, and the derivative of negative 1 is just 0. And it does say to do this in terms of x and y, which we don't have yet. So this should be 1/2 plus our original dy dx. So we could rewrite this as negative 1/2 plus 1/2 x plus y. And so that is our second derivative, negative 1/2 plus 1/2 x plus y. They actually gave you 2 points just for correctly getting that. And then 1 point for your description of all solution curves that are concave up. Well, the question here is, what would make this concave up? Well, what would make y, or what we'll say y minus 1/2 plus 1/2 x greater than 0? Well, any solution, like any description here is good. They usually like something that kind of relates like a linear equation. So let's say y is greater than 1/2 minus 1/2 x. And so if we're looking at points that are above this this line, so all solution curves above the line y equals 1/2 minus 1/2 x are concave up, right? Because the y values need to be greater than that. It cannot be equal to. So they can't lie on that curve, or on that line. And so you got 1 more point here for your justification, or your description. In part C, it says f of x is a particular solution to this differential equation with the initial condition that f of 0 is 1. And we want to know, does f have a relative min, max, or neither at x equals 0? Well, first of all, we have to make sure that dy dx is 0 at this point, or undefined. Because if it's not 0 or undefined, we can't have a max or a min. So we'll first evaluate dy dx at the point 0, 1. So if x is 0, we end up with 0 plus our y value of 1 minus 1, which is 0. So potentially we have a max or a min. And we can determine that really easily because we already have our second derivative, right? And we can just use the second derivative test at 0, 1. Well, our second derivative was, we just had it, it was 1/2, we'll go back and look at it, make sure we get it right. Our second derivative was negative 1/2 plus 1/2 x plus y. So negative 1/2 plus 1/2 of x, which is 0, and then plus y, which will be plus 1. And so that ends up giving us 1/2, which is positive. And if the function is concave up, so we'll say that f of x is concave up, and therefore f has a relative minimum, right? That's what the second derivative test tells us. At the point 0, 1, right? If a function is concave up and has a relative extrema, it's got to be a minimum, right? If it's concave down, it's going to have a maximum. Oh, and that was worth 2 points, 1 for the answer that it is a minimum, and 1 for the justification that it was through the second derivative test. All right, and in part D, the part that is normally our separable differential equation, but that's not what we had this time, they ask us to find the value of constants m and b so that y equals mx plus b is a solution to this differential equation. Well, we know that the derivative of y, that dy dx here, is just equal to m. And therefore, m should be equal to our other dy dx, which is 1/2 x plus y minus 1. Right? So I'm just setting my two different versions of dy dx equal to each other. And since I also know that y is equal to mx plus b, I can now replace this y with mx plus b and get m is equal to 1/2 x plus mx plus b minus 1. And what we can now do is we can just sort of do an equivalence here that the things on both sides have to equal each other. That means that the number of x's that I have on the right-hand side has to equal the number of x's that I have on the left, as well as the constants on the right have to equal the constants on the left. So the number of x's that I have on the right-hand side, if I factor an x out of those two terms, is 1/2 plus m. And then we still have a constant of b minus 1 over here. And on the left, we have a constant of m, but we have 0 x's on this side. So the number of x's on the left has to equal the number of x's on the right. Therefore, 0 x's has to equal 1/2 plus m x's, which tells us that m must equal negative 1/2. Well, the constants also have to equal each other, so m has to equal b minus 1. So b should equal m plus 1, or b is going to be negative 1/2 plus 1, so b will be 1/2. And they gave you 2 points there, 1 for each of the two different values in the end, for negative 1/2 for m and 1/2 for b. And that is the end of this differential equation FRQ, which was question number 5 from the 2007 Form B AP Calculus AB exam. All right, this is question number 5 from the 2008 AP Calculus AB exam. It's a differential equation FRQ. And we get the differential equation y minus 1 over x squared when x is not 0. And the first thing it asks us to do is just sketch a slope field at the 9 indicated points. So we'll note that whenever y is equal to 1, the numerator of that is going to be 0, so dy dx will be 0, since we're excluding values of 0 for x. So we'll just draw horizontal lines whenever y is 1. And then with only 6 points left, we might as well just plug in the values. If we put in 1, 0, 1 for x and 0 for y gives us negative 1 over 1, so a slope of negative 1. Putting in 2, 0 just gives us negative 1 over 2 squared, or negative 1/4, so a very shallow negative slope there. And putting in the point negative 1, 0 is just going to, again, give us negative 1 over 1, so just negative 1 for the value at negative 1, 0. And we'll do the same for 1, 2. At 1, 2, if x is 1 and y is 2, we just get 1 over 1, so a slope of 1. Same thing's going to happen at negative 1, 2, right? Because we're just going to square that negative 1 to, again, get 1. So a slope of 1. And then at the point 2, 2, we end up getting 1/4, so a nice shallow positive slope there. they gave you 2 points for this, 1 for all the zero slopes and 1 for all the other slopes. In part B, they asked us to find the particular solution to this differential equation. And so we've got an initial condition that f of 2 is 0, so we'll have to use that. And this is a separable differential equation because it is a product or a quotient of both x and y, right? It includes the dependent variable in it, and it's a product or a quotient. So we'll start by separating the variables, always step 1. So divide by the y minus 1 to bring that to the left side, and multiply by the dx to have dx over x squared. You get 1 point just for separating the variables. And then you're going to integrate both sides. Both of these should be relatively straightforward integrals, but they're going to give you a point for each of them. So for the y minus 1, right, we're going to let u equal y minus 1, and du is just dy. So this becomes an integral of du over u, which we know is natural log absolute value of u, or natural log absolute value of y minus 1. Normally we'd add a plus c when we integrate, but we're going to ignore that for the time being because we're going to have a constant on the other side, and a constant minus one constant to bring it over just cancels out. So on the left or on the right hand side, we're just integrating, right? This is just an integral of x to the negative 2 dx. Right, so if we integrate x to the negative 2, that's negative x to the negative 1, or negative 1 over x. And now we'll put our plus c, which takes care of the constants on both sides. We get 1 point for each antiderivative, and they even gave you 1 point for including the plus c. To get the 5th point here, you need to solve for the constant using the initial condition. So when x is 2, y is 0, that gives us the natural log of the absolute value of negative 1 equals negative 1/2 plus c. Well, the natural log of the absolute value of negative 1 is just the natural log of 1, which is 0. And we get a constant of 1/2, which we'll plug in here and rewrite the entire equation again as the natural log of the absolute value of y minus 1 equals negative 1 over x plus 1/2. And they're going to give you a 5th point there for using that initial condition to figure out what the new function should look like. And then now we're just going to exponentiate both sides of this to clear off the natural log. So we get the absolute value of y minus 1 is equal to e to the negative 1 over x plus 1/2. We'll clear off the absolute value by just putting in a plus or a minus here, which will then immediately figure out which one we want. So if I plug in 2 for x here, I need y to be 0. So if y is 0, we're going to have 0 minus 1 equals either positive or negative e to the, well, when x is 2, this is negative 1/2 plus 1/2, or 0, so e to the 0 here, which is just 1. So I get negative 1 equals plus or minus 1, which means I don't want the plus, I want the minus. So when we write out this final answer after adding the 1 over, right, we're going to just, we're going to get rid of the plus here. So we're going to have y equals 1 minus e to the negative 1 over x plus 1/2. And that's our final answer there, and that gives us the 6th point there for part B. In part C, it just asks us to find the limit as x approaches infinity of that solution that we just had. So we'll do a limit as x approaches infinity of our function, which was 1 minus e to the negative 1 over x plus 1/2. Well, as x goes towards infinity, this is 1 minus e to the 1 over infinity is 0. So this is just e to the 1/2. This answer here is just perfectly fine. If you prefer to write it as 1 minus root e, that's good too. And you get 1 point for correctly finding that limit. And that's the end of this differential equation FRQ, which was number 5 from the 2008 AP Calculus AB exam.